Let's take a look at what's different about a high-rise structure. Riparian Plaza, located on Eagle Street in Brisbane, was completed in 2005 and is an excellent example of mixed-use construction maximising space on a relatively small building footprint. As you can see, Riparian Plaza has a daytime population equal to a small regional centre such as Charleville, with up to 3,800 people being inside the building during business hours. It stands at 200 metres high to the roof, 250 metres to the antenna, and has 53 levels of retail, office and residential space, with 11 car park levels. It utilises different construction methods and has hundreds of compartments of varying size throughout. One of the features of high-rise building which plays an integral role in fire and smoke dynamics is the necessity to seal the building envelope as much as possible to minimise heating, ventilation and air conditioning costs. This means the environment in which fire or smoke exists may be completely different to the outside environment. Remember, most firefighters in their day-to-day firefighting activity will observe smoke travelling upward. In the high-rise environment, you must understand that smoke can and will travel in any direction depending on the conditions. This session will introduce some of the critical aspects influencing fire and smoke dynamics in high-rise buildings and will include the following sessions relating to ventilation, including wind shear and the effect of wind on high-rise buildings, stack effect, piston effect, and building design and use, including open plan office fires, wind-driven fires, sprinkler effectiveness and auto exposure. Wind has a large impact on the design of high-rise buildings, and wind loading is incorporated into building design. Specialist engineers use wind tunnels and simulations to predict the effect wind has on the shape and height of the building, along with the impact of severe weather events to ensure wind does not damage high-rise buildings. There are several effects that will impact firefighting in high-rise buildings that you should be aware of. The first is wind shear or wind effect. The speed of wind differs significantly in height than can be observed or even felt at ground level. Studies of the effect of wind on electricity-generating wind turbines show a significant increase of wind speed of altitudes as little as 20 metres. Friction or ground effect causes wind to slow down as it passes over the surface and encounters obstacles such as bushland or buildings. As you can see in the graph, wind speed at 20 metres height increases to 6 metres per second and at ground level is still zero. Wind turbine designers must account for this impact on turbine blades to ensure the blades are engineered to withstand these different pressures. Now think of the relationship if you had a building over 50 metres in height and felt a gentle breeze at ground level. Speeds at that height can reach over 50 km an hour and may have a dramatic influence on fire behaviour. Let's now have a look at the computer model simulation of wind impacting a single building with a simulated fire. Observe the airflow around the building, and as the wind strikes the building, it is forced over and around the structure, speeding up as the pressure on the face of the building increases. This also has an effect on the leeward side of the building, causing a low pressure area to form. The smoke behaviour in this case will travel out of the window and be drawn around the surface of the building into the low pressure area on the leeward side. Now let's look at the effect of wind as it passes through multiple buildings. You can see from the blue colour where the wind impacts the building and because of friction slows down to near zero. But as the wind passes between the two taller buildings and then impacts a smaller building, significant wind speed increases can cause massive amounts of turbulent wind to strike the smaller structure. Multiply this effect through a central business district or a coastal high-rise belt and the speed and direction of the wind at height will be very difficult to predict. This can be observed in any high-density environment where winds felt at ground level can appear to come from different points of the compass than prevailing winds. As stated previously, most firefighters in their day-to-day firefighting activity will observe smoke travelling upward. In the high-rise environment, you must understand that smoke can and will travel in any direction depending on the conditions. One of these conditions prevalent in high-rise buildings is known as stack effect. Modern buildings are designed with energy efficiency ratings, and in fact large buildings sold today will have a NABERS rating, or a National Australian Built Environment Rating System. Put simply, NABERS measures the energy efficiency, water usage, waste management and indoor environment quality of a building or tenancy and its impact on the environment. The energy efficiency component is achieved by sealing the building and creating an environment that is isolated from outside weather impacts, to minimise heating, ventilation and air conditioning costs. This design feature has added to the complex phenomenon known as stack effect. When you stack multiple floors on top of one another, you create an artificial environment that is divided into hundreds of sealed compartments, being either cooled or heated for comfort, depending on the outside temperature. When you have a fire or smoke event inside this artificial environment and create openings or paths for smoke to travel, it will cause exaggerated smoke movements that differ from normal smoke travel. Although stack effect is an extremely complex phenomenon and has a multitude of influencing factors, for firefighters it can be simplified to the following. During winter, as the indoor temperature is higher than the outdoor temperature, by creating a flow path into a compartment, you will experience upward movement of smoke and products of combustion. The upward movement of air produces negative pressure at the base of the building and a positive pressure at the top, causing air to be expelled at the top of the building as pressure is equalised. Conversely, during a hot summer's day, the effect is reversed. The outdoor temperature is higher than the air-conditioned inside temperature, so the cooler air is drawn down toward ground level. This downward movement of air produces a negative pressure at the top of the building and a positive pressure at the bottom, causing air to be expelled at the base as the pressure is equalised. So what impact will stack effect have on operations? Well, you observe smoke moving downward or upward through compartments, for example stairwells or lift shafts, and that you must protect the fire-isolated stairwell for occupant egress and firefighter activity. Buildings with stairwell pressurisation will keep the stairs available for escape and firefighting. However, in a building that has no requirement for stairwell pressurisation, such as an office building under 25 metres, positive pressure ventilation must be considered to limit the stack effect. You have to control the stairs before making a flow path for smoke to travel. Elevators or lifts are an integral part of the design of high-rise buildings, and in fact the evolution of the lift enables buildings to be built taller as lift technology improved over the years. There are a number of different types of lifts developed for high-rise structures, but regardless of the design they have an influence on smoke travel within a building and can have a significant effect on operations. The piston effect in high-rise buildings is caused by the travel of lift cars up and down their shafts, be it a single lift in a shaft or a bank of elevators in a common shaft. This picture shows a common type of traction elevator and its features. These include the lift car travelling in guide rails, lift car doors, a cable that connects the lift to a motor in the motor room, a counterweight, and landing doors that open up for a particular floor as required. These landing doors may or may not be smoke sealed, depending on the construction type of the building. It takes a significant amount of money to smoke seal every lobby door to every landing to combat air movement in the lobby where the lift stops, or in fact passes by. When a lift car is stationary, there is no movement of air within the lift shaft. The air pressure within the shaft is equalised above and below the lift car, and in the lift lobbies of all of the floors. When a fire occurs where smoke or byproducts of combustion enter the lift lobby, the simple act of calling down the elevator or bank of elevators will cause the lift in the shaft to travel downward, pushing the air in front of the car and creating a low pressure area behind it as it travels down, acting like a piston. If the lift lobby doors are not smoke sealed, this negative pressure created behind the car will draw air, smoke and or the products of combustion into the shaft as indicated by the arrows. Combined with the stack effect, this can compromise the further use of that elevator due to smoke detector activation in that shaft, ruling out the use of that elevator for further firefighting activities. If in fact smoke has penetrated the lift shaft, entering the lift with firefighting equipment and using the lift in fire service mode to investigate an alarm or conduct a reconnaissance will increase the problem by pushing the smoke that has penetrated the lift shaft into unaffected areas of the building. As the lift car rises, it will push the air ahead of it, creating a high pressure area that could force the smoke into unprotected lobby areas, creating further areas to conduct search and rescue. This may be indicated on the fire indicator panel if present, and present a significant logistical problem for the incident controller. Open-plan commercial buildings offer large compartments for fires to develop, and these can pose a particular hazard to firefighters when making access. Sprinkler buildings can certainly mitigate these risks. However, it's the under 25 metre building that may have fire detection, but no requirement for sprinklers, that will lead to rapid fire development and massive heat release, requiring large flow rates to overcome these fires in the growth phase. The National Institute of Standards and Technology in the United States conducted several experiments involving heat release rates and fire development in 2, 3 and 4-sided workstations, and their impact on fire development in these large open-plan office spaces. Look at the timeline and watch the development of this fire in a 3-sided office workstation. Some excellent research is available on this type of fire development, and this video clip has been sped up, but a glance at the timeline will tell you that if you received an alarm for a fire of this type, you will be arriving as the growth phase reaches its peak and heat release rates are growing exponentially. The turbulent smoke and rapidly growing fire is a perfect precursor to a hostile fire event, and when making entry into this fire and introducing a ventilation point, flow rates in excess of 750 litres per minute would be required to offensively attack a fire at this stage of development. Tactical decisions such as anti-ventilation by maintaining the integrity of the compartment, or simply waiting until you have more resources available for sufficient weight of attack will be a safer option. Tactics such as multiple lines in a coordinated attack strategy before entering and compromising the ventilation profile of this compartment could be an effective strategy. One of the most difficult problems firefighters can face at a high-rise incident is known as a wind-driven fire. Although known about for many years, this phenomenon has not been widely acknowledged, researched or trained for, and experience overseas is that these events have caused multiple firefighter injuries and deaths. Wind-driven fires can and have occurred at ground floor in simple residential dwellings. High-rise buildings, by their very nature, create abnormal, unpredictable airflows, and wind speed is nearly always greater once you work at heights. Wind-driven fire events can be caused by simply opening the door to a fire compartment, or having a window fail after entering. It is important to recognise the potential of these events and the importance of compartmentation and door control, and how it should affect the tactical decision-making of incident commanders and fire suppression teams alike. The following experiments were set up in the United States by the National Institute of Science and Technology to investigate wind-driven fire events and the impact a failing window can have on firefighting. The first experiment is to have the hallway door open as if the occupants had evacuated, leaving the door open and a standard room and contents fire started within the structure. Out of view to the left of the screen, a PPV fan is operating, simulating a 35 km/h wind impacting the sealed window. A thermal imaging camera was placed in the hallway to film the effects of a simulated window failure. You can see the thermal signature recorded by the tick at the doorway, indicating that there is a developing fire somewhere within the unit. Observe the fire behaviour as the fire reaches flashover, causing the window to fail. Conditions in the hallway would deteriorate rapidly and survivability in this environment could be measured in seconds. Now let's look at experiment 2. It's the same experiment, but this time with the integrity of the compartment maintained with the door closed. Note the time allowed for fire development in the room at the bottom left-hand side of the screen, and the vigorous effect of the combustion in the room that the wind has when the window is breached. An automatic door opener was installed to simulate firefighters opening the door to a fire-affected compartment. The simple act of opening the door without controlling the opening creates a perfect flow path for fire and smoke travel into the hallway. Again, survivability would be measured in seconds in this environment. Controlling the compartment and recognising the danger that wind-driven fires present, particularly at height with wind shear and stack effect exaggerating this type of fire behaviour, is key to safe operation. One indicator of extreme fire behaviour is known as smoke tunnelling and requires recognition of this event rapidly on entering the compartment and the integrity of a compartment being compromised. This video shows the internal conditions of the simulated apartment and the developing fire in the room. Note the contents of the apartment are standard furnishings that you could expect in any residential dwelling. The camera on the top left is focused on the fire room. The camera on the top right is focused on the living room toward the fire room. On the bottom left screen is a video camera, and bottom of the right is a thermal imaging camera focused on the hallways outside. You can see the neutral plane about 1.5 meters off the floor with good visibility on the deck. As you would approach the fire room, you would be safe zoning and controlling the environment above and in front of you. Watch the smoke tunnelling effect as the window is breached and air is rapidly entrained into the fire room. The smoke is drawn back into the fire room as combustion is rapidly increased, then travels with explosive speed as it becomes wind-driven, rendering the environment completely uninhabitable. Now observe the visible and thermal cameras in the hallway, and watch both the temperature and smoke levels enter the hallway, making it also uninhabitable to the point of destruction of both cameras. Thermocouples set in the hallway measured the temperatures in excess of 1,000 degrees centigrade. We've now gone from a room and contents to a building well involved in fire. In Queensland, we are lucky to have stringent guidelines that determine when and where sprinklers are installed in buildings. Another experiment conducted by NIST in the US shows the effectiveness of sprinklers in public assembly areas and the effect they have on limiting fire spread. This experiment was commissioned in the aftermath of the tragic Station nightclub fire in 2003, in which 100 people lost their lives. There are a number of contributing factors that cause such a large loss of life, but this shows a reproduction of the stage area and subsequent fire development after pyrotechnics inadvertently set fire to furnishings and the ceiling. With the ceiling insulation vigorously burning and rapidly overcoming patients and causing the room to flash over. Now look at the same simulated stage area, with the provision of 2 sprinkler heads that activate and limit fire spread. You can observe the activation of both heads and the effect they have on limiting the fire. You'll also observe that they do not extinguish the fire completely, and in fact cause smoke and steam to lose buoyancy and the loss of neutral plane due to the turbulent action of the smoke as it rapidly cooled. This video is to demonstrate what internal conditions will be like after sprinkler activation, and the outcome would be smoky internal surge conditions, but the threat of complete room involvement would be mitigated. Auto exposure is the spread of flames on the outside of a building from one floor to the floor above. Flames can be sucked up to the floor above from window to window, causing spread into otherwise unaffected areas of the building. Firefighters entering a window on the floor above a fire from a ladder or fire stairs can have their escape path back to the window cut off by auto exposure flame spread. Nothing highlights the effect of auto exposure greater than an incident that occurred in Madrid, Spain, at the Windsor Tower. Have a look at this short video.
But tonight, the whole thing is in danger of coming down. Fire breaks out on the 21st floor. The result of an electrical short. Nearly 200 firefighters race to save the historical marker. But their hoses can't reach the upper stories. The blaze ravages its way toward the roof of the building. Flaming debris rains onto the street. The neighborhood is quickly evacuated. Emergency personnel work through the night, battling temperatures of nearly 1,500 degrees. Then, shortly after 3 a.m., the top 6 floors collapse. The skyscraper burns and crumbles. By morning, most of the remaining floors have been gutted by the inferno. And soon, all that remains of the building is a smoking steel skeleton. The once towering structure must now be completely demolished after the biggest fire in the city's history. The Madrid skyline will never be the same, and neither will those who witnessed this night of high-rise horror.
Now let's have a look at the Windsor Tower in detail. It has been reproduced in a simulation of how a fire can rapidly spread due to auto exposure, along with design and construction deficiencies, which were in the process of being rectified at the time of the fire. Construction variables such as weather conditions, window thickness, sealant type and spandrel distances will greatly affect fire spread. Spandrel distance is the measurement used to identify the distance between vertical openings on an exterior wall. The greater the spandrel distance, then the less chance of auto exposure occurring. You can see from the simulation that the fire started in a single office, consumed a whole floor, then through auto exposure impacted on the all-glass facade of the Windsor Tower, progressively involving the floors above. The principle that makes auto exposure a threat, particularly in buildings that have small spandrel distances, is known as the Coanda effect. The Coanda effect is the tendency of a stream of fluid to stay attached to a convex surface, rather than follow a straight line in its original direction. As gases or smoke tend to act in the same manner as fluids, it's the hot gases being attracted to the vertical surface as a window is breached. The Coanda effect will influence hot gases escaping from compartments involved in fire by making them follow the surface of the building and impact on windows or openings above. As you can see, by auto exposure more levels of the building became involved, and as more fuel became involved, significantly more heat was released, multiplying the auto exposure effect until the complete involvement of all upper levels, leading to collapse and total loss of the building. This grainy footage from New York was shot on a phone, but it demonstrates some of the auto exposure risks inherent to buildings with unprotected openings above the fire. You can see smoke, heat and flames leaving the affected apartment and impacting on the unprotected openings above. Watch the fire development in the apartment above the fire as firefighters make entry into the fire-affected apartment and hit the room involved. You can see the smoke change colour and turn white, as steam is produced and the main body of fire is attacked. This is known as knockdown smoke. On the levels above the fire, dark grey turbulent smoke is seen to start issuing from the windows above. Whilst construction methods may have influenced fire development in this case, it is a good illustration of fire extension due to auto exposure. This would require rapid recognition and the commitment of further resources to areas above the original fire as fire spreads through previously unaffected areas of the building. Be mindful of auto exposure as a vertical avenue of fire spread, particularly in older style under 25 metre non-sprinkler commercial buildings, and factor this possibility into your incident action plan. In an emergency situation, it is imperative that the QFRS controls and maintains control of all lifts in any building involved. This is not only to stop people not involved in the emergency event becoming part of the problem, but maintaining the use of the lifts for QFRS and emergency services use as a mode of transport for firefighting and evacuation. To take control of a lift or bank of lifts, you'll need a TOC or takeover key. These can be a generic TOC 1 to 10 or building specific if there are secured areas within the building. Building specific keys should be identified on the premises keys and have a detachable key ring. If tasked as a designated lift driver at an incident, the minimum PPE and equipment requirements are full level 2 structural PPE, lift keys, a portable radio, forcible entry tool, and a torch. All other personnel entering the lift in fire service mode should have a minimum of level 2 and self-contained breathing apparatus plus task-specific equipment. To identify if a lift is designed for fire service use, you have to go to the level with the lobby recall facility. Here you will find a fire service key control with a switch that states simply on or off. Turning the key to the on position will ground that lift and or any other lifts in that bank. Multiple banks of lifts will require multiple groundings, but remember, lifts travelling past fire floors in blind shafts can be useful for evacuations. After selecting fire service mode, the lift or lifts in the bank will come to ground and lobby call buttons throughout the building will not operate. When the lift has grounded, you must then identify the lift that has fire service key on the lift car call panel, usually designated by the red key surround, and this will be key to life with the lobby recall facility. As you can see, this lift uses generic TOC 3, and this will be engraved on the outer keyring. Enter the fire service lift with the required personnel and kit, but be mindful of overloading. Firefighters and equipment can be a heavy load. All lifts will have an engraved plate with a capacity in kilograms. Place the key in the car fire service lock and turn to the start position. Select the desired floor on the car selection panel, holding the button whilst you turn and hold the key past the on position to the start position until the doors close and the car begins to move upwards. When the doors close and you are moving, release the key and leave in the on position. Using the lift in fire service mode overrides all the normal functions of the lift, including automatic opening and closing of doors. When you arrive at the designated floor, hold the door open button to utilise the peekaboo facility to check if the floor is smoke locked. When the door opens, have a look at the floor. Release the door open button and the lift lobby and car doors will automatically close. If you detect any smoke, then you can drive the lift to a more suitable level below and set up command and staging areas. If the floor is clear, you can exit the lift by holding the door open button until the door is completely open, and they will remain open until the lift is entered and manually driven using the top key and lift controls. There are a multitude of small variations in the operation and driving of lifts depending on when the lift was manufactured and built. The Australian Standard outlines the common features, and you should encourage your crews to take over the lift, if available, on every alarm investigation to become familiar with these features. Remember, as with all special fire service features in buildings, they are designed for firefighters' use only, so let's use them.